Okay, good morning. Uh, Today I thought I'll do a little bit of revision from the previous section and then go to a new topic called sample surveys and then continue from there. So we will need previous stuff a little bit. But even before that, I thought maybe I should teach you because you can absorb these things without any problem. In this book, it's very, very preliminary level. So therefore, I thought maybe a little bit standard theory, just to mention few things to understand what happens here. So all along we were talking about this drawing from a box, right? And we were talking about drawing from a box with replacement. So that is actually, in real life, that is like taking a random sample from a large population. When you're taking a random sample from a population, of course, we don't do it with replacement, without replacement. But both of them can be considered very similar because in a box is a small one. When you're taking with replacement, it's considered that individual draws are independent with replacement. So when you are taking a sample from a large population, also we can approximately think that observations we are taking one by one, they are independent observations. So this independence is important in basic theory. So I will probably today talk about what happens if you take from a box without replacement. There is some correction that we have to do. But first we usually learn about independence case, right? If you are taking from a box with replacement or taking a sample from a real life situation, taking a sample from a large population. Right? In that case, usually we don't take a sample with replacement, but still both can be considered as together as the same. So anyway, I wanted to just mention two important kind of theorems. Probably you already know these things for the data, but now I'm going to talk about the random variables. A random variable is actually a variable. You know what a variable is generally, right? In mathematics, you talk about variables. When you write down a function, for example, fx is equal to x square plus 2, then we say x is a variable. So in that case, actually, we assign values for x and find out the value of fx, and then we say, okay, f changes with x, therefore, and we can assign values for x. So that is a mathematical variable. In statistics, what we talk about when we talk about a variable, that is some characteristic, right? Characteristic of an item that we are going to observe, like height, weight, gender, that kind of things are just called variables. But when you talk about variable, possible values for the variables, and then also with the same thing, if we talk about the probability of happening each value, that means when you talk about possible values as well as their probabilities, then we go into the next level, talk about a random variable. So in a random, whenever we say random variable, it's a variable with some probability distribution. Probability distribution. So usually we talk about in statistics when you want to do inference and so on. Instead of just variables, we talk about random variables. So suppose x is a random variable. That means it is some kind of characteristic. It changes from person to person, no item to item. X can take some different values. Maybe if it's a discrete one, there are discrete set of possible values for x. If it's a continuous one, x can take any value in a given region, right? In an interval. But in that any case, we can talk about the probability of the values, right? So suppose we have that kind of random variable. And suppose you want to transform this x by say a linear transformation. Suppose y is equal to some constants plus ax plus b, right? Simple linear transformation. Suppose you know theoretically, at least theoretically, you know the expected value of x and the variance of x. These two things are theoretical quantities. Expected value of x is actually something like this. If you assume, for example, if you observe x for on a large number of individuals, their x values will be different, no? Right? So suppose you have a certain population that you are interested in. Suppose you observe x, right? Generally we don't do this practically, but we can imagine what happens. So if you observe x on each and every individual in the population, you'll get different values. Right? So if you find out the mean of those values, and that is what we mean by expected value of x generally. That is a population mean. It's the mean of x values for a whole population. And variance x, by variance x we mean the variance of all those values. So that is also a population quantity. Right? So generally we don't know these things. Because we never observe all the values, all the x values for all the individuals in a population. So therefore, we never know these values. But there are values, right? We can assume that there is a value, and that is a constant for the population. That is a constant. For this also, that's a constant. Right? So that kind of constants whose values are unknown, right? Generally, is some property of a population, are called parameters. So this is what we mean by parameters in statistics. For example, in engineering they talk about parameters in some other sense, right? Not only known, unknown constants, right? So they talk about, sometimes they call parameters for variables also, right? Something that changes. So it depends on the discipline. In statistics, what we mean by parameters are something like this: some population quantities, expected value of a random variable, variance of a random variable, standard deviation of a random variable, and so on. So suppose we don't know this value, but theoretically suppose this is denoted by some Greek letter mu, and this is denoted by some Greek letter sigma square. Sigma is usually used for the standard deviation. So variance will be sigma square. So because we don't know these things, usual standard method is to denote these quantities by Greek letters. It's like Greek, we don't know. But at least there's some value. Right? What we do in statistics is actually we are interested in finding out what is the mean population mean, what is the mean income of people in the population. That kind of questions are important, but we don't know that. So what we do is we estimate, right? That means get a suitable approximation for this value using only a small sample taken from the population. That's what we usually do, right? But anyway, theoretically we denote the expected value by mu, variance by sigma square, standard deviation by sigma, and so on. So suppose x is a random variable whose expected value is mu and variance is sigma square, both are unknown. And suppose we are now interested in some transformation, linear transformation of y. Right? And then theoretically we should be able to get expressions for the expected value of y and the variance of y and standard deviation of y. In terms of these quantities, they will be in these quantities. So one important theorem, or you can call it theorem if you want, is expected value of y is equal to a times expected value of x plus b. So for only a linear transformation like this. And then therefore this will be a times, so let me denote this by mu x and sigma x square because it is for the x. So if I denote this by mu y, for example, y is a new random variable. So if you, there again we can assume that there will be some values for y for each and everyone in the population. So their mean we denote by mu y. So this is going to be a times mu x plus b. So that is one very useful result that we can remember. It's not that difficult to understand. For example, suppose we consider the random variable to be height. So suppose somebody is considering height in centimeters. We can convert it into y, for example, into inches by a linear transformation, right? So if you have some expression for the mean and variance in centimeters, we can easily get it in inches also, right? So like that, if you have a linear transformation, this is one important thing. And the variance of y is equal to what? A square times variance of x. B doesn't come because when you are transforming like this, what is we are doing is we are first multiplying it by a and then adding, right? So ax is a new random variable. So the variance of ax will be a square times the variance of x. When you add b, what happens is the whole distribution shifts, but variability doesn't change. All the values are shifting as it is, only the location is changing, right? So therefore this b will not have any effect on the variance. So therefore we can say, for example, sigma square y is equal to a square times sigma square x. So this is the other important result you can remember. So therefore standard deviation sigma y is equal to a times sigma x. So that has been we were finding always standard deviation and so on. We were using this result without talking about that theoretically. So we were using that. And the second thing is, suppose you have a random variable x, and now we are considering a random sample. Suppose we are taking a random sample from the population of interest, and we observe this x on each of these persons or units in the sample. Right? So suppose we will, in that case we denote, we have to use different notations for x for different values. They are not the same as same x. Right? Observed value will be anyway different, right? From person to person different. So in that case we will be usually denoting x1, x2 up to xn. We say that x1 up to xn be a random sample from a certain population. Right? So the x is actually the observed value of x for different persons. So when you say like that, when you say you have taken a random sample from a population, one assumption is that observations are independent. The other assumption is that this x1 is a new random variable. We don't know, before we observe, we don't know the value. After observing, we know the value. But for example, suppose we have 10 people. X1 by x1, we denote the value that we would get if we observe x on the first person. So in that case, we do before observing, we don't know it. So it's a random variable in that case. It has some probability distribution. The probability distribution of x1 is the same as whatever the probability distribution of x, right? And x2 will have the same probability distribution, okay? And xn will have the same probability distribution. So in that case, we say x1 up to xn are IID random variables. They are independent, identically distributed. Identically distributed means they all have the same distribution, because they are coming from the same population. Random variable. So whenever we talk about a random sample from a certain population, this is what we mean by we have n random variables, say x1 up to xn, which are independent and identically distributed. Okay, so now usually we are interested in some function of these things which are called statistics. For example, let's say t is the sum of these. So it's a function of several random variables. A function of several random variables is called a statistic. There's an even more more theoretical definition, but for us, this is enough for now. Right? So this is a statistic. We talk about the mean, sample mean, not the population mean, sample mean. That is t divided by n. Right? So that is x1 plus x2 plus up to xn divided by n. So that is also a statistic. We talk about sample variance. Usually we write down like this: xi minus x bar square divided by n. Some people use n here, some people use n minus 1. But in the book they were using n here. So that is also a function of the data. So all these are statistics. Because x1 up to xn are random variable, this is also a random variable. This is a random variable. This is a random variable. So any random variable always has some probability distribution. Right? All the random variables have some probability distribution. So we can talk about the expected value of t also. We can talk about expected value of any random variable. So we are usually interested in what is the expected value of this quantity. What is the expected value of this quantity? What is the expected value of this quantity? And also what is the standard deviation of this quantity, right? But in that case, as I explained in the previous class, we don't call it standard deviation. We call it the standard error in this case, right? Standard deviation of a statistic is called the standard error. So we were talking about standard error of the sum of values taken from a box and so on. We were talking about also proportion of values. So when you talk about proportion, always we are considering observations. Our observations as zeros and ones. Because we talk about proportion of people with a certain characteristic. Right? So for example, maybe x is the say height of the people. So we consider x to be the height of a randomly selected person. But suppose I want to find out the proportion of people whose heights are less than 5 feet. I am interested in proportion, in the population proportion. So in order to talk about that now, we have to convert our x into a new random variable. If, for example, you take the first person, assume, now we are not going to measure everybody. Suppose, for example, x1 is less than 5 feet, then our new variable is y is equal to 1. Right? If x1 is greater than 5 feet, y1 will be 0. Right? So that value becomes 1 or 0. For the second person also 1 or 0. For the third person also 1 or 0. Right? So in that case, if x's are all 1 and 0s, what is the meaning of t? T will give you the number of ones in the sample. Right? Number of ones, because all the observations are ones, so you have n values in your sample. So t will be now equal to number of persons in the sample with that particular characteristic, right? Those who are less than 5 feet. X bar will be in that case what? X bar will be the proportion. It will be the proportion because number of people who are less than 5 feet divided by the number of people in the sample. So that is actually the proportion. So when the data are categorized as ones and zeros, t becomes the number of observations with that particular characteristic. X bar becomes p. This becomes p. Right? So they have a sample proportion is a particular is the same as x bar when the data are 0 and 1. So that is another important thing to remember. Okay, now as I mentioned, we can talk about expected values of these random variables. So there is a theory, for example, we can apply expected value of t is equal to expected value of x1 plus expected value of x2 and so on. Whenever there is a sum of random variables, expected value or the mean of that random variable is equal to the sum of the means. So if all these x's are coming from the same population, then all these expected values are the same, right? Because they have the same probability distribution. So this will be, for example, mu x plus again mu x and so on plus mu x. So this will be just n times mu x. Right? So expected value of the, that is like, for example, mu t is equal to n times mu x. Right? So that's what we were using. For example, if you take some values from a box, right? We were talking about the sum of the values in the sample, and expected value of the sum is equal to n times the expected value from the box. So that's where I came from, n times. So this is the expected value from the box, population mean of x. That was one. And then variance of t is again equal to variance of x1 plus variance of x2 and so on plus variance of xn. This one is true always, whether or not x1 up to xn are independent or not. This expression is correct only if x1 up to xn are independent. If they are not independent, in addition to this, there are some more terms coming in called the covariances. Covariance, there are twice covariance between x1 and x2 plus twice covariance between x1 and x2 and x1 and x3, and all those covariances will come in here. Some of the covariances can be positive, some of them can be negative. Right, so that is why independence and dependence are important when you are talking about especially the variance. Right. So if you have a random sample, we assume that they are independent, so therefore this result is valid. So therefore this is sigma square x plus sigma square y, and so, sorry, sigma x1, x2 up to sigma square xn. But all these are coming from the same distribution, therefore all the variances are the same, so let us denote by sigma square x. So therefore this is equal to n times sigma square x. Sigma square t is equal to this. So in the class what we were interested in was not the variance, we were always talking about the standard error. So standard error of t is actually equal to the square root of the variance of t. That's what we were always talking about, we never talked about the variance. And book had given the formula now. It has given what they call the square root law or something. There is no law called square root law, it is coming from here, right? So standard error of t is equal to therefore square root of this thing. That is why you multiply by n, square root n, and then sigma times x. So sigma t is equal to this. Right? So this is the standard error of t, and times square root of this is the standard deviation from the box, right? Population standard deviation. Right. Okay, so let us apply the same idea. If we want, for example, to talk about expected value of x bar, right, using the same theorems, same results, we can derive, we can show whatever we have discussed already, we can just understand how it comes. So expected value of x bar, that is the sample mean. So here we are talking about the mean of sample mean, population mean of sample mean. What do I mean by population mean of sample mean? Sample, in order to get one sample mean, we need n x values. Those x values coming from the original population. Original population. So here we talk about expected value of x bar. So that is the mean, population mean of x bar. Expected value is always some population mean. Right? So how do we understand this? expected value of x bar means there is actually, now for the population expected value of x, we can easily understand that. Right? If you want to get expected value of x, if you want to find out it, it's still possible in some cases. If you observe x for all the population quantities, you will have x for all the items. Then if you just add them up and divide by the number of items in the population, you can find out this. Right? But if you want, you cannot easily get this one like that, because there is no existing population for x bar. There is no existing population. It's only an imaginary population for x bar. So what we mean by this expected value of x bar is kind of a mean of an imaginary population. How this imaginary population will arise is like this. If you say, for example, observe simple n x values, take a random sample of x values from the original population, you can calculate x bar. So suppose you keep it and then you do it again. If you do it again, usually we don't do it like that, we take only one sample. But we can imagine what will happen if you do it again. So if you take another n values from the original population, your x bar will be somewhat different from the previous x bar. Suppose now you keep it again, so now you have two x bar values. Right? X's are coming from the original population, you are looking at possible values of x bar. Right? So if you do it again and again and again large number of times, you will see large number of possible x bar values. Large number of possible x bar values. Right? Remember, we don't do this practically, but we can imagine what will happen if you do it. So in that case, if you do it again and again and again, a population of x bar will be generated. A population of x bar will be generated. Now by expected value of x bar, we mean the mean of that population. So that is the kind of an imaginary quantity. Right? What will be on average x bar if you look at all possible x bar values. Right? So anyway, we can easily get an expression for this in terms of the expected value of the original population like this. So we know that x bar is equal to x1 up to xn divided by n. So this is going to be x1 plus x2 up to xn divided by n.
Use this pen, I think it will be easier.
මේක පටන් ගන්නකොට ඉතින් දැන් එකක් තමයි මේකේ තියෙන කුණු මේකට එනවා ඒක වැයෙනවා. Right, so this is again applying the previous result for any x expected value of say y is equal to a times expected value of x plus b. Right, so we have a similar thing for individual ones here. This divided by n, this divided by n, this divided by n. So if you apply that result here, you can say this is expected value of x1 divided by n, expected value of x2 divided by n, and so on. Expected value of xn divided by n. But I don't know the way. Right. So all these are mu x values. Right. So mu x over n plus mu x over n like this. Mu x over n. So that is equal to mu x. So that is an important result. Expected value of x bar, that is the mean of that imaginary population that would be generated if we repeatedly sample from the population and generate the distribution of x bar. The mean of that imaginary population is the same as the mean of the original population of x values. So expected value of x bar is equal to mu x. This is a very important result in the sense, for example, what it says is the mean of x bar is equal to mu x. So that means if you consider possible values of x bars, right, they are going to be distributed around mu x. Right? So if you show that by this axis x bar values are, it's a variable, it can take set of values in a range. But if you consider the mean of all those possible values, they are going to be around mu x. Expected value of x bar is equal to mu x gives us some idea like that. So that is why we usually say x bar is a suitable quantity to use as an estimate for this. Right? So for example, if your x bar is somewhere here, then you take that as your estimate for this quantity. So in that case, of course, there is an error in our estimate. If the distribution is very far away, then there is a possibility that our error can be large also. There is a small probability. But we will look at another important result, and that's why we will see why x bar is considered the best estimator for the population mean in a minute. So that is one reason. Therefore, we know that x bar is always distributed around the mean of the data. Therefore, we can use x bar as an estimate for the mean of x. Now let us look at the variance of that x bar. So by variance of x bar we mean again the variance of all the possible x bar values in that generated population. It's kind of again variance of an imaginary population. So we can we can show that this is equal to 1 over sigma 1 over n square, because this is variance of x1 plus x2 plus up to xn divided by n. So make it in x1 divided by n, x2 divided by n, x1 up to xn are independent. So this is like variance of x1 divided by n plus variance of x2 divided by n up to variance of xn divided by n. Because of the independence, we can write down like that. Now variance of constant times a random variable is equal to square of that constant times the variance of that random variable. So this is 1 over n square variance of x1 plus 1 over n square variance of x2 and so on. 1 over n square variance of xn. So this is going to be n times sigma square x divided by n square. So that is equal to sigma square x divided by n. So variance of x bar is equal to variance of x divided by n. So that is more important practically. What it says is, now if you look at this distribution of x bar, we know now it is distributed around the population mean of x values. But this one says variance of x bar is smaller than the variance of x. It depends on n inversely. Right? When you increase n, the variance of x bar becomes smaller and smaller. So that means if you have, for example, suppose the distribution when n is equal to 10, distribution of x bar. So if you consider the distribution of x bar when n is equal to 100, it will be something like this. So that means now x bar is very possible values are very mu doesn't change. Expected value of x bar when n is equal to 10, that is mu x. The expected value of x bar when n equal to 100, that is also mu x. Right? It's always centered around mu. But the variability becomes smaller and smaller. Therefore, that is a good thing, because if you have a large sample, if you use that x bar as an estimate for mu, you can be sure that with a high probability that you will be close to the population mean. So that's a very good thing. Therefore, the probability of large errors will be almost zero. Right? All the errors will be quite small in that case. So those results are important results to remember. So we have now obtained expected value of t is equal to n times mu x. Variance of t is equal to n times sigma square x. So that is about t. And then also we have shown that expected value of t is equal to, so let me denote by Tn here to just to denote that we are talking about n values, sample size is n, right? Because this quantity always depends on n, right? So Tn is actually the sum of n values, right? So expected value of Tn is equal to mu x is divided by n. Variance of Tn is equal to sigma square x divided by n. So that is another important result to remember.
So x exponential.
What are the
The T again should be exponential.
method T again, sorry. Yeah, method exponent. Thank you. We are talking about exponent. Mean, sorry. So now from this we can easily get expression for expected value of P and variance of P. Suppose P is, we are considering a particular property, right? We want to know what is the proportion, simple P is the sample proportion with that characteristic in the sample, right? P. We use the sample proportion as an estimate for the population proportion. So, but we can, as I mentioned, P will be equal to x bar if our data are zeros and ones. P will be equal to x bar. So, in that case, suppose now our data are zeros and ones. x1 is a 0 or 1, x2 is a 0 or 1, and so on. So, 1 means that particular item has the characteristic that we are looking at. 0 means it doesn't have that characteristic. So, what will be mu x in that case? Mu x, population mean, right? If all the x's are zeros and ones, 1 represents the characteristic that we are looking at, 0 represents no characteristic. Right? So, what will be mu x in that case?
The number of, the average of the number of people with that characteristic.
Yeah, number, not the number in that case. Mu is the mean of, so number of people in the population. Number of people in the population with that particular characteristic divided by the population size. That will be the mean population mean, because all these are ones and zeros. No? So when you add them up, it will be the total number of people with that particular characteristic in the population. You divide by the population size. So that is what you call the population proportion. Population proportion. So if you denote the population proportion by, say, for example, some other Greek letter, say theta, then expected value of P should be equal to theta, where theta is the population proportion. Again, theta is an unknown quantity because it's a population mean, kind of a population mean. Whatever the population quantity is, we don't know. Right. So according to this thing, therefore expected value of the sample proportion will be equal to the population proportion. So that's why sample proportion is a good estimator for population proportion. So therefore P will be distributed around theta. Right. What will be the variance of P? Here sigma square x over n. So in this case, what will be sigma square x? So we can use that, there's a simple formula to calculate. We are given, if you have only two types of observations in a population or in a sample, you can use a particular equation, right? So in this case, we have in the population, we have zeros and ones, right? So what is the formula that we, or you can use the previous formula, the original formula, that is sum of, in that case it will be sigma square x. Remember, this is the population quantity, right? If x's are zeros and ones, still the same definition will apply. I from 1 to capital N, because we are now calculating for the population, assuming population size is capital N. So xi minus mu x. Mu x will be in this case theta. Xi's are going to be 1 or 0. Xi's are going to be 1 or 0. Right? Because and divided by square here, divided by capital N. So that will be the sigma square x. So if you want to calculate it like that, then you have to take your observation minus whatever the population theta square divided by. Or so from that you can get an expression, simple expression in terms of theta. But it will be easier to use the formula given in the book. If you have only two types of observations, it says sigma x in that case is equal to large number minus the small number times the square root fraction of the large number times the fraction of the small number. There was a formula like this. So that is the standard deviation. When your x's are in this case special case zeros and ones, but even if you have some other two values, still you can apply the formula. So if you apply this formula here, what will be the expression? Large value in our zeros and ones, large value is 1, this is 0, right? Square root, fraction of large values, right? Fraction of large values in the population, that is equal to theta, population proportion, theta. Right? So if there are theta proportion of ones, then 1 minus theta proportion of zeros. So therefore in this case sigma x, right, when x is equal to 0 and 1, this will be the standard deviation. So that will be the population standard deviation. So that will be, so we have to take sigma square x will be square of that. So therefore the variance of p is equal to theta times 1 minus theta divided by this n. So that is the variance of the sample proportion. So the standard deviation, in this case standard error, we call it the standard error because p is again a statistic. Standard error of p is equal to square root of this, that is theta times 1 minus theta over n. So those are some important results that they are useful results. For the total, for the sample mean and sample proportion. Sample proportion is a special case of the sample mean. Okay, so I thought maybe this will be useful in the university, for example, if you are learning statistics somewhere. Okay, so then at the end of the last class we talked about now here we were talking about only the expected value and the variance. We were not talking about the distribution of t, distribution of x bar, distribution of p. We didn't talk about the distribution, we were just talking about two qualities of characteristics of the distribution. Now these two will be enough to describe the whole distribution. If for example the distribution of the random variable Tn or distribution of x bar or distribution of p was kind of symmetric, then mean and variance are enough to describe the shape of the distribution and so on. Get an idea. But it's not always like that. If the observations in the population observations, if the distribution of the population is skewed, then these quantities will also have a skewed distributions, right? Not necessarily symmetric. Right? Generally, if we are obtaining data from some skewed distributions, for example, x bar will have a skewed distribution as well. But the central limit theorem is important to find out the distribution of these quantities if n is large. If n is large. If the sample size is large. So if n is small, as I mentioned, usually the shape of the x bar distribution and the distribution of Tn, distribution of P will roughly mimic the shape of the original population. That means the distribution, shape of the distribution of x. But if n is large, according to the central limit theorem, and we saw that in some simulations in the previous class, the distribution of Tn, distribution of x bar, distribution of P converge to a normal distribution. So that means if n is large, Tn will be approximately normally distributed with this mean and this variance. Right? If n is large, the distribution of x bar will be approximately normal with this mean and this variance. Right? If n is large, the distribution of P will be again approximately normal with this mean and this variance. So that is the important thing. Once you know the distribution, then we can calculate probabilities regarding what is the probability that the total will be greater than something, what is the probability that T total will be less than something. That kind of probabilities can be calculated. And actually, the word that I mentioned is not really correct. You cannot actually calculate it because still these quantities are unknown quantities. No, mu x is unknown. So whatever the probability expression will going to contain these quantities. Right? So but you can get expressions for the probability in terms of unknown quantities. Right? But practically what we do is, once we get these expressions, we substitute. For example, if the expression contains mu x, we substitute x bar for that. Get an estimate for that quantity. If the expression contains sigma x, then we substitute sample standard deviation for that. Right? If the expression contains theta, then we substitute p for that. P is observed, so we have a value, so we can get approximations. So that is what we do. So the central limit theorem is a very preliminary way of saying the central limit theorem, and it talks about only the sum. So it says when drawing at random with replacement from a box. If you are drawing from a box, this theorem will be valid for with replacement case, because when you are drawing from a box, if you are taking it without replacement, observations will not be independent, they will be dependent. But the theorem will be applied only for the independence case. So this is particular case, right? If you are taking a sample from a box with replacement, then the sum of values in the tickets, for example, will have approximately a normal distribution. So that is what it says. So according to this, if I come back to this one, this is the total, right? So what it says is, if you take a random sample with replacement from the box, and if you look at the sum of the numbers in your ticket, right, that will be approximately normally distributed with n times mean, n times the mu x means, in that case the mean of the population, where the population in the box. So that's why n times the mean of the box. And the variance of that will be n times variance of the box. Standard deviation will be square root of that. So that's what you were talking about all along. And if you standardize your total, so Tn minus the mean divided by that will have approximately a standard normal distribution. But the more mathematically correct central limit theorem is this one. It talks about the distribution of the sample mean. Sample mean. So we are talking about this quantity. Here the general one is not about taking from a box. Box is only a model. So here this one says in general, more general. Suppose you have a random sample from some population. practically meaningful population. So in that case, you are assuming that your observations are coming from a large population. N is relatively small compared to the population size. So therefore, we can consider x1 up to xn are independent, and they are identically distributed. They all have the same distribution. So in that case, suppose the population mean, that is the population of x values, mean is mu and variance is sigma square. Usually those are unknown quantities, but let us denote them by mu and sigma square. And mean has to be finite because this is a mathematical importance, because there are theoretically we can create some distributions or populations whose mean is infinite, right? So for that kind of situations, this theorem will not apply. But most of the practical situations, of course, almost all the practical situations, populations have finite means. So therefore, this theorem is valid. So x bar n is the sample mean of n observations, and this theorem says the standardized x bar n, right? X bar minus the mean of x bar divided by the standard deviation of x bar, right? Mean of x bar is mu, right? So if you subtract this and divide by the standard deviation, that is the square root of this, sigma over root 10, then that quantity will converge to a standard normal distribution. So that is what the theorem says. So this happens actually when n goes to infinity. It's a limit theorem. But of course, in practice, we don't have situations where n is infinity, right? So therefore, we don't have in practice situations where this theorem will valid exactly, right? Only thing is that we can use it approximately with some large, if the n is large, then we can say x bar n minus mu over sigma over root n is approximately standard normal. Approximately standard normal. So that is important, because that will tell you that if x bar n minus mu over sigma over root 10 has an approximately a normal distribution with mean 0 and variance 1, this from this we can show that x bar n will be approximately normal with mean equal to this value, and variance will be, usually we write down the variance in second term, so this will be sigma square over. So that is the practically important result. What then pan in the board? So this theorem is very, very important because this is valid for any kind of population as long as population has finite mean and finite variance. So you may be drawing from a population where the population itself has roughly a normal distribution. Then definitely, actually, if you are taking this x1 up to xn from this kind of original population, in that case x bar will be normally distributed even n is equal to 2. If the x1 up to xn are normally distributed, x bar is always normal. It's not approximate, it's exactly normal. That is not important when you are talking about central limit theorem. Central limit theorem is important especially when the original x's don't have a normal distribution. That is where the central limit theorem is useful. Suppose x's has something like this distribution, uniform, right? So like between 5 and 10, probabilities of x's are roughly the same. We say that kind of distribution is a uniform distribution. Suppose this is x. If you are taking observations from this kind of population with this kind of distribution, then x1 up to xn all have uniform distributions. Even if x's have a uniform distribution, if n is large, then x bar n will be approximately normal. So that is the importance of the central limit theorem. And similarly, even if the original distribution is something like this, very, very positively skewed, you have this kind of, one example is something called exponential distribution. We have this kind of shapes for the original distribution. Right? So x's will have this, all the x's are coming from this kind of distribution. But still, if n is large, we can show that x bar is approximately. Right? So even if x's are coming from something like this, positively skewed, we have, there are so many models for this kind of shape. One is gamma distribution. Gamma. There's another one, log normal. So many models. Right? There are situations this kind of populations have this kind of shape. Even if your all x's are coming from this kind of shape distribution, still x bar n will be approximately normal if n is large. So that is the importance of central limit theorem. Why knowing that it is normally distributed is important? Well, we are interested in seeing again calculating probabilities. What is the probability that the sample mean will be less than something, greater than something, and so on, those kind of probabilities. In order to calculate the probabilities, we need to know the distribution. Right? So if n is like 2 or 3, we will not know the distribution of x bar n. We don't know. Right? If n is large, then by central limit theorem it tells us that it's going to be normally distributed. So you can use the theory that you know about the normal distribution. So that is a very useful result therefore. The central limit theorem. Now, at the end of the last class, we were talking about how large this n should be for us to assume that x bar is normally distributed. How large n should be. But generally, we say if n is sufficiently large. If n is sufficiently large, x bar n will be approximately normal. But how much is sufficiently large depends on the shape of the original distribution. Right? How large n should be for x bar n to be normal depends on the original shape of the distribution, shape of the distribution of your excess population. So as I was mentioning, for example, if the original population was itself normal, then as I mentioned, even n equal to 2 is enough. X bar is exactly normal in that case. So that is not an important case for us. But if, for example, it is symmetric, right? If the original distribution is symmetric, even if it is flat like this, it is symmetric, right? Then you don't need that much n to be large for x bar to be normally distributed. For example, in this case, n equal to 10 may be enough. Right? When n is equal to 10, x bar is approximately normal. Not only this kind of one, even if, for example, even if it is not normal, but say suppose, for example, this kind of symmetric, still it will work for a rather small number of observations. But of course, if the original distribution is skewed like this, for example, then you will need probably at least 50 or maybe even 100 observations for you to be able to use this result. Right? So therefore, many people generally say they have actually observed this by considering real practical cases, by looking at the practical distributions, even if the practical distribution is somewhat skewed. If it is not very skewed, usually n equal to 30 is enough. That's what they have empirically observed. So therefore, whenever people talk about the central limit theorem, this magic number 30 comes up, right? So it's not actually magic number. You have to be careful when you are using it, because you have to know that for this to be true, n can be even very large if the original distribution is very skewed. Right? So you have to get some idea about the shape of the original distribution before you think about how long you should have a sample size for you to be able to use the theorem. So that is a very important thing. 30 is just mentioned most of the cases because it applies for most of the cases, but there are situations where 30 is not enough. Right? Even if n is 30, still x bar will have right, like this kind of distribution. It's not normal, it's still skewed. Right? So if you increase n further, then it will be coming to something like this. Right? So that is an important thing to remember. Okay, so we will take a small break and then